Alright, so let's talk about acetals. And just like before, I'm going to go ahead and start off drawing a general reaction here. So we have species there, and I go ahead and I react this. And I'll just change colors to show that what I'm working with here, with two equivalents of an alcohol. What I get out of that reaction, an equilibrium, and I make sure that I'm running this under acidic conditions. In my product, at least, I'm going to see if I can fit this in here. Oh, switch colors. So that is what I'm going to get as an overall reaction. That's my acetal. So let's draw out these individualized steps for this reaction. Note that this is an equilibrium reaction, which kind of lends itself. So we start off with an aldehyde or ketone, just like we have with damn near every other reaction that we've talked about so far. I'll go ahead and draw in my lone pairs. And I'm running this under acidic conditions. It doesn't really matter. I'm just going to use the generic form for that, HA. I don't really care what type it is. And so mildly acidic, or acidic conditions, not mildly acidic, gives us protonation of our keto, the oxygen in our keto group. And this reaction exists in equilibrium, just like when we had talked about with hydrate formation. This is a very similar reaction to hydrate formation. So I'm just going to go ahead and put that as my oxygen there. This oxygen now has a positive formal charge that is existing there. And if you want, again, you can draw the resonance structures of this. I would highly advise that you do that to explain the reactivity of it. But the species is now, just like with hydrate formation, whenever we protonate it, it's now so unstable that alcohol can act as a nucleophile to attack it. So I'm going to go ahead and just draw it almost like as if it were a bent structure to show that it's similar in reactivity to that of water. And so it flows there. We have movement of electrons here. This reaction existing in equilibrium. We have a positive charge on our oxygen here, and like always, we don't want to have that around for too long, so I'm just going to go ahead and draw my generic conjugate base from the initial proton transfer reaction, stealing a proton off of the alcohol. We're now at our reaction intermediate, so I'm just going to label this as my intermediate species, sometimes called a hemi-acetal because it's a halfway acetal, and for reasons that I don't quite fully understand, this is considered a very unstable species. It is unstable. I kind of tried to drawing resonance structures and explain why this is unstable, but I know hydrates are unstable as well, but I'm just a little iffy on that. Someone smarter than me can probably answer why this is so unstable. But anyways, the next step being just as the other one would be a proton transfer reaction as well. So I'm running this again in mildly acidic conditions. Here's that there. And you should note that this is existing in, I guess, equilibrium, but this mirrors the same type of reactions that we were doing when we were forming hydrates. So we now have a water leaving group on a tertiary carbon, and I kind of like to think of these as SN1 type reactions here. And so it's going to do just that. It's going to leave, forming a tertiary carbocation. And I said over here that I have two equivalents of an alcohol. I've used up the first one, now I'm going to use up the second one, which this reaction, obviously, because it's a carbocation and not a partial charge, is going to be a much faster reaction. And it does just what any lone pairs are going to do. It's attracted to the positive charge on the carbocation. And once it attacks there, you have a positive formal charge on your alcohol. I think you know where I'm going to go with this. And once again, we have a proton transfer reaction where the conjugate base of whatever acid we had started off with is going to deprotonate the alcohol. This gives us our final product of our acetal, or the one that we're looking for. This is the reactive species that we're looking for. So one of the things that you should definitely keep in mind about these reactions is the nature of equilibrium. This reaction will not proceed very easily. This first step here will not proceed very easily if you're not running it in acidic conditions. This reaction totally mirrors the hydrate formation. Alcohol is very, very similar to water. This has similar pKa's. They have similar reactivities. And in terms of this, they can hydrogen bond. All this stuff makes them very, very similar. And so this reaction is very similar to hydrate formation. Keeping in mind Le Chatelier's principle and keeping in mind the pKa's will definitely help us understand how we can get this reaction to proceed to a specific point. So one thing that I also wanted to mention, though, about an acetal is acetals are not ethers. Okay, an ether is where we have an R group on ether side of an oxygen, but not whenever it's given this unique structure here. They are not ethers in terms of nomenclature or ethers in terms of their reactivity. So just keep that in mind. All right, so now I wanted to move on to cyclic acetals. And the thing that I find really interesting about these is that the reason that we would make a cyclic acetal is because they make really good protecting groups. So they are protecting groups for reactions. Remember when we had talked about protecting groups for other, I think with using carbanion nucleophiles and bases, we talked about using a silyl ether and an ammonium salt, and that's just kind of, it's not a reaction that we really understand. It doesn't even give us the details of the mechanism about what the consequences would be of treating it with the removing group. But with cyclic acetals, these make really good protection groups where we can understand the mechanism behind it and understand how we can form it. So I'm just going to go ahead and just start off with what we're drawing as a generalized overview. But what these always tend to form, at least in a cyclic acetal reaction, is either a 5 or 6 membered ring. 5 or 6 membered ring is going to be formed. Why? Because anything less than that or greater than that becomes thermodynamically unfavorable. We tend to use a unique type of acid, our acid identity for this type of reaction. We tend to use toluene, TSOH, or paratoluene sulfonic acid, and run this reaction in situations where we also treat it with a dihydroxy acid, such as ethylene glycol. So that's the generalized overview. Now let's get into the nuts and bolts and draw the actual mechanism. So let's say that I start off with some type of an aldehyde. And the example that I think I'm going to use is 5-hydroxypentanal. So there's the OH. I go ahead and run my 5-hydroxypentanal or some type of a compound that can do an intramolecular reaction. I also make a note that these are intramolecular reactions. And so I can obviously have it in this conformation here, but notice that if I, say, apply some heat or something that's going to warp the structure of the molecule to where it's not just a straight flat chain that we're seeing here, I'm not going to draw that for visual purposes, but just keep that in mind. And I'm obviously running this just like with any type of an acetal reactions. I'm running this under acidic conditions. And just with any type of an acid, you get a protonation of the oxygens on your keto or aldehyde group. Just like with the last time, we have a positive formal charge here, and we're running this reaction in a unique species here, and going to have a attraction to that. Again, I'm putting this under, say, like some type of heat or some circumstances where it just naturally folds into a different conformer, but I'm so lazy, I'm not going to draw that. Also helping if you draw the minor resonance structure to explain this mechanism here, but anyways, what we get through an intramolecular reaction is the formation of a ring. So intramolecular, I'm just going to put that in here, ring formation. And that ring is always going to be either a 5-person or a 6-person ring. Just like with the last reactions that we had been talking about with regular acetal formations, we end up forming a positively charged oxonium ion from the initial transfer that takes up the burden, I guess, of having the positive formal charge. And the conjugate base, or you could just think of it as any type of a generic base, I'm just using this as the conjugate base of our first acid here, is going to deprotonate that alcohol, thus getting us more of our starting material, keeping us in track here. So what we get out of that is our next intermediate of, and I don't know if you can tell just by looking at it, but that is a hemiacetal. It's a cyclic hemiacetal, but it's still a hemiacetal, and that's still going to be our reaction intermediate. And so just like all the other tens of trillions of reactions that I've consistently drawn here, we have another acid here. You can think of it as this one that was just formed. Obviously this is existing in equilibrium, but we're going to pour ahead a lot of acid in this to make it go forward direction equal in terms of equilibrium. And so it's going to do what all acids do and protonates the OH group. Oxygen now having a positive formal charge is not going to be very happy, and just like before, is a leaving group to go ahead and leave. So you may be thinking in terms of thermodynamics that these reactions aren't nearly as favorable because of this being a secondary carbocation, but just know that we have this oxygen here that we didn't have with the previous ones. Well, actually it was listed, I just didn't come across this point that obviously the lone pairs are going to be able to stabilize that carbocation more so than if it was just another carbon group. But just like before, we now have a positively charged carbocation, and we go ahead and we bring around whatever our generic alcohol is going to be that we want to run this in, ethanol, methanol, we don't care. And it's going to do a nucleophile attack. You could, again, think of this like an SN1 reaction. We now have a positive formal charge on our oxygen. Bases don't like to see that, and they don't like to be in that state, and we end up having a proton transfer reaction, and I'll see if I can fit it down here right at the very bottom. But what we get out of this reaction, it's existing in equilibrium, is our acetal, our cyclic acetal. And since that's my final product, I'm just going to go ahead and circle this in red. That we have now done this reaction towards equilibrium. Obviously, acidic conditions, keep things in mind. Don't forget Le Chatelier's principle, and it's always very nice. You may want to draw it, I guess, the intramolecular reactions, be comfortable drawing this in the ring conformation or in the chair conformation as well. But just keep that in mind. And always, whenever you're, this step right here is confusing for a lot of people. Always number your carbons to do this. So I have carbon 1, 2, 3, 4, 5. I know that in this reaction that the 6th species in my chain is going to be bound there, and we end up getting our ring here. That's something that just always bothers a lot of students. So cool.